Okay, today we'll do integrals. Um, some of them will have a natural log in them, but most of them will be rational, and then the antiderivative of a rational function is going to be natural log. So we have reviewing, we have the derivative of natural log is 1 over x, and so the antiderivative of 1 over x is ln x. We need an absolute value there, and we also have the constant of integration. So let's look at, since the antiderivative is pretty easy, we're just going to look at a lot of integrals that require substitution. All right, so here we have u, x, and u evaluated at the limits of the integral. So let u equal the denominator. The differential of u is 3 dx. So dx is du over 3. We don't need this. Well, we won't need it, but we won't know it until we substitute. And we don't need this because it's indefinite. There are no limits. So we have 1 over u, that's u, and then dx is du over 3. And we have 1/3 integral of 1 over u du. So that's 1/3 ln u plus c. And then substitute for u, 3x plus 2. All right, pause the video and try that one. U equals x equals u evaluated at a. Let u equal the denominator, and du is dx. We don't need this, and we don't need that. 1 over u, dx is du. So we have ln u plus c ln x minus 5 plus c. All right, let's just make it a little more complicated. And sometimes we just maybe don't recognize what's going to happen. We'll just try letting u equal the denominator and see what happens. If we expand the numerator, we see this. And if the coefficients are correct, then this will end up being the derivative of that. Sometimes you just try it and see if it works. So there's, got a little messed up. U evaluated at a. All right, so u equals the denominator. Du is going to be 3x squared plus 6x. The derivative of 4 is 0, and we'll have times dx. Du over 3x squared plus 6x is dx. And substitute so that the numerator is x squared plus 2x, and the denominator is u. Dx equals this. And why don't we just factor out a 3, x squared plus 2x. And that's what makes it work. We have that canceling. We'll have a 1/3 integral of 1 over u du. And that'll be a 1/3 ln u plus c, 1/3 ln, and then u was x cubed plus 3x squared minus 4. All right, and pause the video, try this one. So hopefully you saw that we need to be flexible with integration strategies because we can't always use the same one. And this turns out that we're not going to use the natural log here. If we let u equal the whole denominator, then we're not going to be able to cancel that. It'll make it more complicated. So if we just let u equal the inside of the denominator, now we have du equals negative 2x dx. The derivative of this is negative 2x, so dx is du over negative 2x. U to the 1/2, and then we have du over negative 2x. So we substitute for dx. dx is du over 2x, and then the x will cancel. And now we have negative 1 over 2 u to the negative 1/2 du. Add 1 to the exponent and divide. Oops, we don't have that anymore. We have that. So add and divide, we just copied that. 1/2 divided by 1/2, that cancels. And canceled that, we have a negative, and it's going to be u, which is 3 minus x squared to the 1/2, or negative radical 3 minus x squared plus c. Here's another type of question that shows up with natural log. And this is where the numerator has a higher degree than the denominator. So before we integrate, we have to do long division. And we'll think of what multiplies by x to get x cubed. So I'll put x squared times x is x cubed. X squared times 5 is 5x squared. Negative 5x squared minus 6x. What multiplies by x to get negative 5x squared? And that'll be negative 5x times x, negative 5x squared. And this will be negative 25x. So we're going to be adding that, and we have 19x. So we multiply by 19 times x to get 19x. 19 times 5, 95. Subtract. And there's the remainder. So we rewrite the integrand as x squared minus 5x plus 19 plus the remainder over the divisor. So we have x squared minus 5x plus 19 plus negative 115 over the divisor. Now we can integrate each of these terms, and then we could use substitution with this. But here there's nothing to cancel, and so we can just do that mentally. We're going to have x cubed over 3, 5x squared over 2, 19x, negative 115 natural log x plus 5 plus c. So if you don't see how to do this, then do substitution with all the steps, and you'll see that that's going to be the integral. So here we have another problem that requires long division. Try that one. Pause the video. And we need to get x cubed, so we'll multiply by x. X times x squared, x times 3. Put that over here. So x times 3 is 3x, and we'll subtract. Bring this down. Subtract. Now multiply by 3. Let's multiply by negative 3 and negative 3 times 3 x. That'll be a plus, and we get 0. So there's a remainder of x. We have the integral is going to be x minus 3 plus x over x squared plus 3 we can do the antiderivative of these, and then we'll do substitution with this. If we let u equal the denominator, du is 2x dx, dx is du over 2x. So just focusing on that, we have, we could write x squared over 2 for this, minus 3x, or negative 3x, and then we'll have x over u. So u is x squared plus 3, and then we just copy the x and substitute for dx. dx is du over 2x, and we'll cancel the x's. One half x squared minus 3x. Here we have a 1/2. We have 1 over u du, and 1 over u gives us ln u. But u is a function of x. So I substitute for u. U was x squared plus 3, so we have x squared plus 3 plus c. All right. So here we have to be a little creative. It's not going to be the same substitution that we've been doing in the other examples. We have to be a little creative. If we let u equal the whole denominator, it's not going to work. So then we try letting u equal part of the denominator. So x du equals dx. Also, we have a definite integral, so it has to be u evaluated at e squared. So that's ln of e squared, and that equals 2. U evaluated at e is ln of e, which is 1. And now we have a new integral from 1 to 2, 1 over x times u, and then dx is x du. So the x's cancel, and now we just have 1 over u du. 1 over u is ln u. So we don't have to write the constant of integration. We don't have to write c anymore. We also don't have to substitute back for x, because these are u values, and we can just write ln2 minus ln1, which is ln2 minus 0. We get ln2. Okay, pause the video and try that one. Now, sometimes when we have two terms in the numerator, we have to split this up into two functions. It's possible to rewrite it like that and then integrate that. It's not necessary for this problem, but just remember that if the substitution doesn't work, you can always break it up into two functions. But with this problem, let's go ahead and, so we're not going to do it that way. We're going to leave it like that. And let's just try letting u equal x plus 1, du equals dx. We need to find the u value at x equals 1 and the u value at 0. The limits are 1 and 0, so let's find the u values there. Put a 1 in there, we get 1 plus 1. Put a 0 in there, and we get 1. So now we have from 1 to 2, x minus 1 over u du. But with this strategy, we have an x that didn't cancel. So that's why we have this, so that we don't forget that this is an option where we just isolate x, subtract 1, and now we can substitute for x. X is u minus 1 minus 1. And that is u minus 2 over u. And here, well, now we can separate it. U over u is 1. And then let's just have it be plus negative 2 over u. So we broke it up into u over u and 2 over u. U over u, 2 over u. This is u evaluated from 1 to 2, and this is going to be negative 2 ln u from 1 to 2. So we'll substitute 2 here, and we get a 2. Put in a 1, we get a 1. Put in 2 here, we have negative 2 ln 2 minus negative 2 ln 1. And 2 minus 1 is 1. This ln 1 is 0. So this is just going to be 1 minus 2 ln 2. And we'll stop there.